at which on which graphs this algorithm will fail, and what are the options we have after that. Okay. All right. So try Dijkstra's algorithm on this graph. I'll give you 1 more minute to complete. Everyone, try to find the right path. So you have to find two things. One is the path, okay, from your source to any of the vertex, and second is the weight of that path. Okay, both the things have to be found. Anyone who needs more time? Sai, are you done? All right, so let's see the execution of this algorithm. So in this algorithm, what is there is, So I'll start with the basics again because I think last class also we did only one problem, right? So the source that is there, you'll assign 0, 0 value to the source, and rest of the value becomes infinity. Okay? And you'll take two arrays. One is the visited array, and this is for 1, 2, 3, 4, 5, and 6. Okay? And this is the parent array. This is null, 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 and null. Okay? Sorry, not 0. There's no vertex named as 0. So we'll start with 1, 2, 3, 4, 5, and 6. Okay. So now the algorithm is similar to what we had in Prim's algorithm. What you have to do is from 0, you have to look up at all the adjacent vertices which are directly connected with the vertex 3. Okay. And you have to assign okay. So if this value plus this value, that means for 5, if this value plus this value is less than the current value, current key value at 5, then you will replace the current key value at 5. Okay, that's called the updation method. Okay, so what you do is again you check. So 0 plus 8 is less than infinity, of course, so this is modified as 8. Okay, then 0 plus 3, this is also okay, this is also infinity. Oh, 7 I did not. Okay, 7, let's say 7 is here. Okay, 7 is here. All are 0. And here is 7. A little bit clumsy, but fine. So 0 and this 7 is there. So 0 plus 4 is 4. So 7 becomes 4 and 0 plus 5 becomes what? 5 for vertex 1. That's it. Only 3 vertices are there. So now out of the all the remaining vertices, okay, whichever vertex has minimum value, that will take order of v time. Whichever vertex will have minimum value, you basically finalize that in the single source shortest path, the graph. Okay, so this is finalized. All right, so now we are going to process 4. So that means the parent of 7 is what? 3. Okay, the parent of 7 becomes 3. All right, now and 3 is visited, and then 7 is also visited. Now for 7 you have to start analyzing. So 7 is actually okay. It is connected to everyone. So we'll have updations everywhere. Okay. So first let's start with what? 7 and 5. So 4 plus 3 is equal to 17, right? And 8. So 8 is still less than this. So I'll not update this guy. Okay. Now talking about node 6. Node 6 is 4 plus 10 is equal to 14, which is less than infinity. So this will become 14. All right. Next is 4 plus 7 is 11. So 4 over here becomes 11. Okay. Now you have what? 4 plus 7, which is what? 11 again. This becomes again 11. And now you have 4 plus 3, which is 7. But here we have a 5. Okay. Here we have a 5. And you have to remember this also. Okay. So here we have a 5. So that's it. Okay. So now I think I've taken care of everyone. Yeah. 7 is connected to all and I've taken care of all. Now from the remaining vertices, because 7 and 3 are already processed, from the remaining vertices, check the key pair value. Okay. So the key pair value, the minimum key value for the vertices will be 7, 5, 11, 14, this, and I think this is, okay. So 5 will be the one. Okay. That means sorry, and one more thing I forgot to tell you, that whenever you update the value, you have to update the parent as well. Okay, so we'll do this as well. Okay, so 6 parent will be what? 7. Okay, because 14 value was updated by 7. 4 parent will be 7, and 2 parent will be 7, and 1 parent will be 3. Okay, one parent is 3 and 3 doesn't have any parent, and 5 parent is what? 8. So it was what? 3. Okay, so whenever you update the value, you have to update the parent as well, otherwise we'll not know at exact point of time who is the parent of whom. Okay, so 0 and 5. Now 0 and 5 is there. This is the minimum, so I'll assign, okay, this is the next path. All right, and now we are going to process 1. So now we'll visit 1 and process it. Okay, so that means for 1 is also done. Now from 1 all you have to do is visit the other nodes. So 1 is adjacent to what? So let's first complete for 6. So 1, the value is 5, 5 plus 5 is 10, and 6 is 14. Okay, so this becomes 10, and the parent of 6 becomes, the parent of 6 becomes 1. Okay, so now this is 1. Alright, everyone is clear till this point? Just respond, because the graph is really complicated and it will take little longer for me to explain. I hope everyone is following. It's little difficult to teach this online, but I'm trying my best. Okay. All right. So 1, Sai, you also following, right? So once adjacent vertex is 6, we have completed that. Now once adjacent vertex is 7. Okay. 7 is already processed, so no need to take care of it. Okay. And how about 2? Okay. So 5 plus 1 will be 6. So now this value will be updated to 6, and later on you'll update the parent also. So parent of 1, parent of 2 becomes 1. Parent of 2 instead of 7 becomes 1. Okay. Now I don't have anything, so this is again done. All right. Now you find the minimum among the ones which are left. So 2, 4, this 6, 11, 10, and 8. Yeah, so 6 will be minimum. So basically you'll try and join this path now. Okay. Because of this path, this is the updated one now, because 2's parent was 1 now. Okay. So you'll add this in your single source shortest paths graph. Sai, are you following? Yes or no? Now you will process 2. Okay. So now 2's adjacent vertices are 7. 7 is already done. 1 is already done. 4 is not done. Okay. So 6 plus 6 for 4 will be 12. But 11 is already less. Okay. So you will not make any modification. Hence the parent will also not be modified. And that's it. So that means 2 doesn't have any one. So during when we are traversing for 2, there is no update which is made. Okay. So based on this, we can say now we have to find again the minimum out of these. So 8, 10, and 11. So 8 is the minimum now. Now we are going to process this. And the parent of 3, see which node you have to add in the single source shortest path graph is, you check, you're now processing 5. So you check the parent of 5. 5 parent is 3. So you add this node. That is why I want to make sure that whenever I update the value, I update the parent as well, so that it becomes easier for me to find the path. All right. So now 5 is being processed, and 5's adjacent are 6 and 7. 7 is already completed, 3 is already completed, and 6. So for 6, I have 8 plus 12, which is 20. And we have already 10. So 10 is less than 20, so I'll not modify. That means no changes are made. All right. Now 10 and 11. 10 is minimum, so we are going to process this. And 10, let's see the parent of 6. Parent of 6 was 1. So basically this path will be included in the graph. Okay. And we are going to process 6. 5 is processed, now 6. Okay. So now 6 is what? The only node which is not processed till now for 6 is what? 4. So that means 10 plus 3 and 11. You will compare 10 plus 3, which is 13, with 11. Since 11 is already less, we will not modify or change the key pair value, and then 6 is also processed. So let's say now 6, who is the parent of 6? 6 is parent of 6 is 1, and now you're going to process 4. All right. So when you process 4, I don't have any one which is not processed, so 4 as it is, and you check the parent of 4. 4's parent is 7, so you modify this. So this is the graph that you will obtain. Okay, so you start from 3 and you choose any of the red lines that I have drawn. Okay, anywhere you start from 3 and you choose the red line, so that will make sure that you get minimum path from a single source, that is 3, to any vertex in the given graph. Is this algorithm clear to everyone? Minimum distance to the other vertices will be the source vertex. No, Sai, so minimum distance, see, if I am at 3, okay, from 3 I can take up these paths. And how can you find these paths? When you code the Dijkstra's algorithm in your system, na, you maintain this array. So basically, let's say from 3 I want to, so from, let's say I am at 6, okay, and I want to reach my source, okay. So from 6, You take 6 parent is 1. Okay. Now you go 1 parent is 3. So that means 6 to 1, 1 to 3. So basically you are doing it in the reverse order using the array. Alright. So there is no need to actually see, when we are not doing this in a system, we can draw this array and it would be easy. But when we are doing something in the system now, it becomes difficult for us to draw this array. Alright. Okay. Sanjeev, I want to ask one thing. Is there any way to share the screen in this tool? Okay, but it is saying that screen sharing is not supported in the browser. Okay, maybe in other browser it is possible. Okay, okay, but it's not letting me share screen over here. Okay, fine. So I hope this algorithm was clear to everyone. Okay, so let us again try for another graph, which is again little complicated. Okay, so this is your other graph. Okay, now try to use Dijkstra's algorithm in this graph. Try to implement it. Let me know once you're done. Gayatri and Sai, have you completed? Okay, okay. Take a minute, complete it. All right. I think everyone has completed. I hope everyone got the right answer. So let's see the solution again. Okay. So why I wanted to do a lot of problems on this is because this is an important algorithm, and it's a difficult one. Okay, it's a difficult one. So when you try and implement this algorithm in your computer, okay, because when you'll set for your placements and all, most of the algorithms they'll ask you white paper coding for it. I hope everyone knows what is white paper coding. Okay, so during that time, if you are aware that how to run this algorithm on a given graph, it becomes little easy for you to code it, okay, from scratch. That's why little implementation like this would help you a long way. All right. Okay. So let me again. How many here I have? Oh, I have taken different vertices. Okay. So let me just. I'll not take the visited one. Let me just take the parent one only. Okay. But do not always take the visited one as well. So parent, I have one node, null parent, two node, null parent. Then I have three, 1, 2, 3, and then 7, 8, 9, 12. 4 is there. Let's say 4 is there, then 7, then 8, 9, 10, 11, 12, 9, and then I'll take here. Okay, 11 and 12. These are my total nodes that I have, right? I'll just draw the parent graph over here. Now they are saying to start from 7. Okay, so you start from 7. That means the parent of 7 will always be null. Okay, you assign 0 and infinity to everyone. Now you check the adjacent vertices to 7. So first adjacent vertex is 9. Okay, so you update 0 plus, I think this is 11. Okay, 0 plus 11, so this becomes 11, and the parent of 9 becomes what? 7. All right, now from 7 you have another 2, 3. So 0 plus 6 is less than infinity, so this becomes 3, and the parent of 3 becomes 7. All right, now 0 to 2. Okay, again parent of 2, and this value becomes 2. All right, and 0 7 to 1 also, so this becomes 7, and the parent becomes 5. The key value for one node, one vertex becomes 5. Okay, and what all I have? 1, 2, 3, 4. Yeah, I've taken care of all of them. Okay, so this is my current condition of the graph. Now find the minimum, and the minimal will come out to 2. Okay, so basically this is your vertex. Now you'll start processing 2. Okay, so 2 is only connected to 7 and 1. Okay, and 2 plus 3 is 5, and 1 is already at 5. Okay, so you really don't have to do any updation. Okay, so yeah, this is it. So 2 is processed. This is done. This is done. Now you'll process what? Remaining. Out of the remaining, find the minimum. Minimum is 5. So next processing 1. Okay, so now 1, 2 is already processed, 7 is already processed. Now you'll process 8. Okay, one moment. Okay, so 8, from 1 to 8 if you go using the edge 9, so that means 5 plus 9 is 14. This is infinity, so this becomes 14. And the parent of 8 is 1. Parent of 8 is 1, and I have updated the value. Now from 1 I have another update to 3. So that means 5 plus 4 is 9. 9 is greater than 6, so no update will happen. I'm good to go. So I have processed 1 as well. Okay. This is processed, this is processed, this is processed. Now out of the remaining I have 14, 6, 11, infinity, infinity, infinity. Okay, so 14, 6, 6. 6 I'll process now. So when you process 6, out of that 7 is already processed. All the adjacent vertices from 3, 6 is the value for that vertex. Okay, so from 3 you're going to process 7 already done, 1 already done, 8 is not done. So 6 plus 8, 6 plus 8 is 14, and 8 already, the vertex 8 already has 14. So no need to update this value. We are good to go. This also edge is taken care, this, and now the last edge is from 3 to 12. Okay, using the edge which has weight 12. So you'll have 6 plus 12, which is 18. So this becomes 18. All right. And the parent of 12 is 3. So parent of 12 is nothing but 3. Okay. And that's it. All right. So this is also processed. Now remaining you have what? 14 is there, 11 is there, and 18 is there. So I'll process 9 now. Okay. Vertex 9 will be processed. So, okay, so 9 is connected to 7, no need to take care of that. 9 is connected to 4. So that means 11 plus 9 is what? 20. 20 is less than infinity, so I'll update. And parent of 4 is 9. Parent of 4 is 9. Alright. And 9 is also connected to 11. So 11 plus 8 is equal to 19, so I'll update this as 19. Okay. So the parent of 11 will become what? 9. Okay, these are the two updates I'll happen. That will happen. Okay, yeah, I'm done over here. Now all you have to do is process the remaining. This is also processed from here: 14, 19, 20, 18. So I'll process 14. Okay, now if you see, 8 is connected to 3, which is processed. 8 is connected to 1, which is also processed. So I don't have to take care of anyone. That means this is automatically at its shortest distance from the source. Okay, now you have 18, 19, 20. So we'll process this one first. Okay, so when you process this, 12 is already taken, the vertex 3 is taken care, then 4. So 18 plus 3 is 21, which is greater than 20, so you'll not modify. Hence this is also processed. Now you process 11, okay? And 11, 19 plus 7 is what? More than, of course, 20, so it will be 26. Okay, so 11 also will not make any update, and 4 will also not make any update. Okay, so these values are the shortest part, and this tree this particular array will give you the whole path for from any vertex to the source. Okay, it will give you path from any vertex to the source. Now if you check, let's say we are at 11. 11th parent is 9. 9th 9th parent is what? 7. And then 7 is the source, right? Yeah, 9th parent is 7, and 7 is the source. So every time you can find the path from this particular array. All right, so is this explanation clear to all of you? Yes? All right, so next is, can you try and find the time complexity for this algorithm? Can you try and find the time complexity for this algorithm? Now we have seen what is the dry run for this. So now please try to find the time complexity. Just change the slide. One point you have to remember is this particular graph, okay, this particular graph is stored as an adjacency matrix, okay. In the last class, I told you there are two ways to store any graph. One is adjacency matrix, and second is adjacency list. So this graph is stored as an adjacency matrix. Right, there is no requirement of the graph. I'm just asking what will be the time complexity in general for any algorithm. Sanjeev, let's use the terms V and E. Okay, V is the number of vertices in a graph and E is the number of edges. All right, anyone else who found the time complexity for this algorithm? I would like to ask the explanation as well, okay? Whosoever answers, please be ready with the explanation also. That will help us understand the time complexity better. All right, so anyone else who needs more time to solve this? Come on, people, just give me a response. Do you need more time or should I discuss this? All right. So Sanjeev, how did you get order of n square v square? Tell me.
Yes, sir. So in matrix, in the worst case, a particular node might be connected to every other node, and we might need to check all of them.
Right.
So therefore, one node to all other nodes may be connected. So that would be n into n minus one. And
Correct.
since in a matrix we will be checking every edge at least twice, so therefore we'll divide it by two. So that would be n into n minus one divided by two, which would be n squared, order of n squared. I mean, if n is considered as a vertex.
Okay. Okay. Yeah. Sounds just about right. Okay. Let me just consider the v part also in this e part. Okay. So I want to write in terms of v and e both. Okay. So see, what you're doing is run this algorithm in your mind. See, that's why we do these dry runs so that you will know exactly how much time it will be taken. Okay. So run this algorithm in mind. What will happen is in the worst case, I will have a complete graph. Right. Now, what is a complete graph? Complete graph is a graph where every vertex is connected to remaining n minus one vertices. Correct. So in a complete graph, you will have order of v square edges. Okay, order of v square edges. That is what is happening. Okay. Now you see what you are exactly doing is at every particular vertex. Okay, when you are at every particular vertex, you are actually checking the edge. This update equation. Let's say d of current or let me not write d. So key of current vertex plus the weight, the edge weight of u comma v is less than or equal to uh, key value of the next vertex. Okay, this is the update equation. This is the update condition, I will say. You are checking at every vertex. Okay, so in the worst case, if one particular vertex is connected to every vertex, so those connections will be what? V minus 1, correct? And you're doing this for all the vertices, correct? Right. So basically what you're doing is for all the vertices, you're doing this. And see, even if I don't have these many edges, still, now, okay, let me just concentrate on this first, then I'll concentrate on the next part, okay? So you're doing it for V minus 1 edges, okay? And next time also you'll actually do for V minus 1 edges and so on, correct? So basically, can I say something like this? This you are doing for nothing but total edges, twice into total edges. Everyone understood this part? You're checking the update equation 2 times for every edge in the graph. Is this part clear to everyone, or do you want me to repeat this once more? Okay, so we are doing this for every edge because when we are checking this update equation, we'll check it edge by edge. Once, so let's say something like this, these two vertices are connected, right? Once you'll process this vertex and check this condition for this edge, next time you process this edge and check the condition for this again. Okay, so basically in the worst case, you'll do this for 2 times. Now the second part which will contribute to your time complexity is actually you're finding the minimum out of the remaining edges, remaining vertices, right? Out of the remaining vertices, you're trying to find the minimum. So when you are at your source vertex, so now n minus 1 vertices are there, out of which you have to find the minimum. Okay, so you'll use v minus 1 because see, these edges and vertices values are not sorted. Okay, and there is no way you can sort because every time you process some node, some of the values at some of the vertices will get modified. Okay, so sorting will not be a solution for this. So v minus 1. Then you process. Now, after v minus 1, two nodes will be processed. Total processed nodes will be 2. And then v minus 2 will be the remaining from which you have to find the minimum. Similarly, v minus 3 and so on till 1. Okay. Now this becomes what? V into v minus 1 by 2 order of v square. Okay. So now the total time complexity is dependent on two parts. One is this guy calculating minimum, and remember this is a adjacency matrix. Okay, this is an adjacency matrix, and this is why order of v square is required. Okay, now trying to find the minimum using this, and the other part is v. Okay, where you are trying to use the update equation. This is the total time complexity for Dijkstra's algorithm using adjacency matrix. Everyone understood this? So it's very important that you write both the things because both the things are contributing to the time. That's why I've written this. But see, the worst case is that edges can go up to v square, right? So ultimately, it gives you v square only. The worst case is edges can go up till v square. So ultimately, it gives you v square. But I wanted to write this in this form just to separate out the two tasks which you are doing and which are contributing to the time complexity. All right, so let's go to the slide again. So I think I have the same thing slide on the slides. So in the matrix to find the shortest path, every node of the vertex, it finds the minimum distance of remaining node from the source. This is what I've just discussed, okay? But I've not written the first part, okay? So I've just written this thing, but actually this will be the time complexity. All right. So I hope this time complexity is clear. Now we are going to see if we can do better. Okay. We can actually do better if we use adjacency list. Okay. But when Edges are this much. Okay, I'll tell you why. See, let's try and get some intuition as to how this thing will be correct. Then we'll go deep into the algorithm and how things are actually done. Okay, let's try to get some intuition out of it. So when you're actually doing something like this, what is happening is, I told you the time complexity is E plus V square, right? Now when you're doing this, so E is what? E is the time taken for updating the equation, right? Checking those conditions and all. So now tell me one thing. Tell me one thing. That particular time in which you check the condition is totally dependent on E, correct? Number of edges, right? That part is not dependent on the data structure I'll choose. Yes or no? Is this clear or not? It's a simple update equation. Na? You are checking that update equation twice for every edge, right? Now it is sure that that particular update equation, since it is dependent on the edge itself, so it will depend on the number of edges, not on the data structure, right? Which you are using to store the edges. Okay. So if my number of edges are order of v square, then what will happen is, even if I try to use an intelligent data structure and try reduce it, the time complexity will still be order of v square. Is this point clear? Yes. If you are finding time complexity for the whole algorithm, okay? So that is why what we want is, if we are using adjacency list, we want the number of edges, to be order of v. Okay, that is why I've written number of edges should be order of v, and this is the reason behind it. So that this guy will not be the one contributing to the time complexity. This guy should be the one. Okay, so if this is order of v, let's see how much we can reduce this guy. All right, okay. So now can you think of something which will help us reduce this? Yeah, good. Sanjeev, good. Heaps, good. What should I do? My target is simple. My target is simple. Reduce v square part. This part na, to calculate minimum after every iteration. Anyhow we have to do, see, v iterations we have to do, right? For every time, for v times we have to calculate the minimum. Before we were actually updating, we were using total v comparisons, right, to find the minimum. That was a 1D array similar to that. Can I reduce this v or not? Now heaps is a good data structure. You can use min heaps. Now my question is, how will you use min heaps? That's the next point, and that is the next algorithm itself. So I want you to think before I discuss. I want you to think it, because I know there are, I know everyone can think this. How can you reduce this V? Number of comparisons I need to be less. Anyone who comes up a solution, feel free to discuss with me, either on chat or on call. Sanjeev, any idea how will you use min heaps? I'll give you that the answer is min heaps. But now the thing is, how will you use it? Okay, priority queue is fine, but here there is no priority which I store na. Here what I have to see, if I use min heaps here, I'll give you a little help. If I use a min heap here, all I have to do is I have to store the name of the vertex and I have to store the key value, right? Associated with every vertex. That's what I have to store. All right, okay. So let me just give you some hint. Okay, let's try and reach the solution together. See, first of all is I'm using a min heap. What am I storing in min heap? I'm storing what? A particular data structure, which is what? Here is the name vertex, okay, or vertex value, whatever it is. Here is the key value for that vertex, and here you'll have the pointers and all. Okay, so these two things I'm storing, the name of the vertex and the key value. That's what I'm storing now, vertex and key value, right? Now, can you tell me, if I try to build a heap, min heap, out of these, how much time will I take? Only for key values. Remember, only for key values I'm doing it. V, correct? I'll take order of V time. Okay. Now see, I have this min heap with me. Let's say something like this. Okay, I have this min heap. Now this min heap, this will be the source, correct? Because the value, and see, you'll basically sort the min heap based on the value, correct? So this will have the minimum key value, and hence you can simply say that this will be the source, correct? Now when you take out source, what are you actually going to do? You're going to check all the edges which are connected to that source. Yeah, so all the edges you will see, let's say this source, there are three edges connected to the source. Okay, so for each edge what you're going to do is, you for each edge, you know that that edge from source to which vertex it is connected, right? So the next task will be finding that vertex inside your min heap. Yeah, please guys, this is little complicated, so please understand this and please give me response. After some point of time. Okay, regularly. I mean, okay. So now this vertex this vertex will be there inside this tree. So every time you actually uh, try to check this edge, whether this edge should be included in the single source shortest path or not. So you'll try to find first this edge in the tree. So how much time will I take to find this edge in the tree? Okay, no Sanjeev, log v is all right now. There's no need for log e because there are v vertices, right? So log v time to find the vertex in min heap, because it may happen that the vertex was already processed and it will not be there in min heap, right? This might also happen, so you need time to find the vertex also. Now once you have found it, okay, find the vertex. Second is check key value, right? Now you will check the key value because you know what is the key value of this vertex, which is right now being processed, and you know the key value of this guy, and you know the weight of the edge also. Okay, so you'll check what is the weight of this guy and update update the key value if required. Everyone clear? All of you will update the key value as and when required. This is the second part. And update accordingly. And update accordingly, right? And the third thing is now, if that value was very small and let's say that value is very less and all, so you have to heapify also, na? Now the third thing will be heapify. Are these three steps clear? First, find the vertex which is there at the min heap, okay, wherever it is. Second is check the key value of the vertex, okay, and update accordingly. I mean, if it has to be updated or not. And now if it is updated, then you have to heapify. So worst case, let's say every time it has to update. So worst case is you'll heapify every time. Heapify will again take order of log v time, correct? And this will also take log v time. So what I am trying to say is, in nutshell, this whole procedure takes what? Order of log v time. Clear to all of you? Yes or no? Now, if you look at this, you're basically see every time you encounter an edge, you are repeating this process. Correct? Every time you encounter an edge, you are repeating this process. So what is happening is finally I'll write the time complexity. Okay. So that E part is there only. Okay. That is not modified. But when you use Minheap as a data structure, now you're actually doing this in E log V time. Is this true? Because for every edge, I'll say this, okay? For every edge, twice you're trying to check it, and then worst case is that you'll have log V operations to be done for every edge. This is clear, yes or no? Everyone. So now, if E is equal to order of V, okay, not V square, then let's see what the time complexity becomes. It becomes V plus 2V log V. So this becomes order of V log V. And this is why this becomes order of V log V. And this is how you are able to reduce, but the given constraint is that your number of edges should be V, not V square. Is the algorithm, the procedure, how I used min heap and how I calculate the time complexity. These four things clear to everyone, yes or no? See, Sanjeev, in fact, I created your notes and all, but today morning I was looking at some questions, and I think in 2019 or 20 they have given a question similar to this. All right. So they'll modify the question, and based on, they'll say, okay, you're using this data structure. Now tell me what will be the time complexity. So you have to, and I can tell you one thing, min heaps or heap data structure are very important. Are very important. In fact, algorithms is less important compared to data structures. Heaps are one of the best data structures that you can have. Okay, they provide you, you know, uh, I mean, arrays. There is a problem like deletion and insertion in the middle is not really easy, but that's not the problem with linked list. Okay, you can implement a heap data structure using a linked list, but heaps are really important. So they are asked something like this in GATE exam. Okay, so Sai, log V you understood? Okay, so see, I am doing this log v task, this task that I wrote in this slide, this task for every particular edge, right? Because I will take the minimum vertex, I will take the vertex with minimum key value, and I will see, okay, this vertex is adjacent to how many edges, right? Yeah, to find the vertices it is adjacent to, correct? And this I'll do for all the vertices now. So at maximum, see, although I'm doing it for V vertices, that's correct, but at maximum there are E edges in the graph, na? So if you have an edge, right? If you look at this, if you have an edge, okay, something like this. So when you're processing this node, you'll consider this edge, right? And when you're processing this node, you're considering this edge again, right? So every edge in the graph will be considered twice, and that's the maximum you can have for a particular edge. So if I say that there are E edges in the graph, so totally 2E times you're doing this procedure, the procedure that I just mentioned, this one. You're doing it for 2E times, right? So that means 2 into E into log of V. 2 into E into log of V, this. Alright. Okay, so I hope this is clear to everyone. So let's just see what we have in the slides. I've written the same thing, I think. Okay, so create a min heap of size v where v is the number of vertices. This we all know. Every node of min heap contains vertex number and distance of the value. So distance of the value, or I'll say key, whatever we are saying, right? Initialize min heap with source vertex as root, and distance is assigned to infinity, and you create the min heap. Okay. While min heap is not empty, do the following: extract the vertex with minimum distance. Okay, and then let the extracted vertex be u. Now once you extract the vertex, for every adjacent vertex of v of u, okay, all the adjacent vertices, check if v is in min heap or not. If it is in min heap, then you check for the distance. So checking whether this is in min heap or not, you have to go log v down. Okay, log v time will be taken to check. Now you have to take the distance. Checking the distance over here and updating it would be constant. And now you have to, okay, I have not written anything about heapify. Okay, and once you do this, update the distance, and third would be heapify the tree. Okay, this I've already mentioned in the time complexity part. Third would be what? Heapify the tree. Okay, so now the time complexity is what? This to create min heap. And basically for each edge twice try to check if we need to update the value or not. Okay, so this will be what? Value or not, and heapify it. So it will again take log v. Okay, I've combined step 2 and step 3 in this slide. So finally the time complexity is order of v plus order of 2e log v, which is nothing but order of e log v. Okay, now if e is v square, see, if e is v square, order of v square, so then this gives you a worst case, even bad than the previous algorithm, min heaps. Okay, you have to be really careful of what kind of, how many edges do I have in a particular graph. This will give you even worst case than the previous one. All right, so I think everyone should be clear on this. Okay, now what I want is try to implement Dijkstra's algorithm for this graph. Okay, and consider your source node is 1. Okay, source node is 1. Try to implement Dijkstra's algorithm. This node is 1. These are all infinities. So Sanjeev, yeah, to answer your question also, they'll not ask to write the code or something like that. They have not asked like codes of Dijkstra's algorithm like this. But what they'll say is, let's say you are using, okay, this data structure is being used, okay, and this is the current state of the system, right? Using this data structure and all. Now try and insert a node in the current graph. Okay. So what will happen to the whole Dijkstra's algorithm? Okay. Or you try to delete a particular node from the graph. They like to play with the concepts and like to modify things. And based of so that's why the whole procedure, only if you just remember the time complexity and you don't know how you have obtained, then it would be difficult for you to implement it. That's why we try to do a lot of dry runs so that you can derive time complexity anytime you want, because they'll not say, okay, find the tell me the time complexity for Dijkstra's algorithm using a matrix. They'll not tell that. What they'll say is, okay, you are doing this modification in the current graph. After this modification, how much time more will be required to again reset and get the correct graph? Something like that. So when we'll come to the questions now, you'll see a lot of different kind of questions which are asked on MSTs and Dijkstra's algorithm. No, so missing part of algorithm, they don't ask. So they'll ask for simple data structures like linked list and all, but they have not asked for like Dijkstra's algorithm, because see, Dijkstra's algorithm has only the update equation. If I talk about the code, it has only the update equation, right? So if you just remember these update equations, that's also all right. They'll not ask you complicated codes. Definitely, they're not going to ask you that. Because every topic has some speciality or has some quality things to be asked from. And Dijkstra's, Bellman Ford and all, these are more of asking some numerical question, because I cannot form a numerical question on linked list. I have to just give you the code, right? So in those things they ask you like, okay, linked list is there, fill in the some statement will not be there, some condition will not be there in the uh, original question, and they'll tell you to fill in the statement, or fill in the correct condition, which will run the code without any error. All right, so I think everyone completed this. Okay, so let's see this algorithm. Okay, now I'll again choose 1 as the vertex. Okay, and I'll again only do it for I'll only create my array for this parent thing. Okay, only for the calculating the correct parent. 1, 2, 3, 4, 5, and 6. All right. So parents are null, and now you start from 0. So 0, and which are the adjacent vertices? 0, 3. So this becomes 3, and the parent of 2 is what? 1, and 3. This becomes 5, and the parent of 3 is what? 1. All right. That's it. Now you're going to consider 2. Okay, we'll consider 2. So 2, 3 minus 2 becomes 1. So this guy becomes 1. All right. 3 minus 2 becomes 1. And the parent of 4 becomes 2. Then 2 is at here. So 3, this will be 3 plus 1, which is 4. So this becomes 4. And the parent of 3 is 2. All right. And yeah, that's it. This edge is already processed. All right, now I'm going to process 4. Okay, so this path is fixed now. I'm going to process 4. So 4 plus 7 gives you 8. Okay, but 4 is already less, so I'm not going to process this. I'm not going to process. 1 plus 3 gives you 4. So parent of 5 is what? 4. Parent of 5 is 4. Little clumsy here, but just try and manage. So parent of 5 is 4, this is done, this is done. So that means we are actually good to go. 4 is also processed, this is also processed, this is also done. Now 4 is there, infinity, 4 is there, and that's it. 3 more are left, right? So let's process this guy. So when you process this guy, weight is 4 and the child parent of 3 is what? 2. So this edge will be processed, done, okay? So now 3 is connected to what? 5 and 3 is connected to 6. So 4 plus 6 is 10. 10 is greater than 4, so I'll not do anything. And now 3 is connected to 4 plus 5 is 9. So this will be updated as 9 and parent of 6 becomes what? 3. Alright. 4 and 9. Process this. Okay. Process this and then all you have to do is, and this I think 4 will come from here, right? Yeah. So this guy will be the next edge added. So now you update this. Now see, 4 plus 4 is 8. So 8 is less than 9. So I'll update this also. And the parent of 6 becomes 5 instead of 3. This becomes 5. Okay. And finally, when you process this, this will be the link. Okay. So now this thing is clear to everyone. Yeah. And one point that I want to tell you is just note here we have a negative edge. Okay. I just want to tell you here we have a negative edge. Okay. Now try for this question. Try for this one. Try for this one. Sai, have you completed? Okay. Now, anyone noticed anything here? Anyone? Something weird about this graph when you apply Dijkstra's? What happened? Tell me what happened. Exactly. In fact, Sanjeev, can I say all distance turned out to be minus infinity? Yeah. So let me just try and run the algorithm over here. Okay. See. So let me not maintain the parent this time. Okay. Let me just concentrate only on values. Okay. So see, let's start with again. This has the infinity and we'll concentrate only the key values. So 0 plus 3, this becomes 3. 0 plus 5, this becomes 5. Now we will process this guy. Okay, this is already processed. So 3 minus this becomes minus 7. Alright, minus 7. And then 2 and 1 becomes 3 plus 1, this becomes 4. Alright, so now 4 and minus 7. Minus 7 is less, so you process this. So when you process this, minus 7 plus 3 becomes what? Minus 4. Minus 7 plus 7, this becomes 0. Okay, this is even less. And that's it. Okay, and see, now if you see here, minus 7, this is already processed, but minus 7 and minus 10, if you're saying, okay, so this guy is actually becoming what? Minus 70, correct? Minus 17, right? Or let's say let me not process something which is already processed. Okay, let me not try and process that. Okay, so this is becoming minus 4. Now this is again 7. So this became 0. Now you'll process this guy. Okay. Now since this is 0, now see 0 plus 1 and this was 3, right? So 0 plus 1, it will again become what? 1. Okay. Now again if you see 1 minus 10, this again becomes minus 9. Minus 9 plus 7, this again becomes minus 2 and so on. See, the problem over here is this, this and this. If you check this cycle, the net weight of this cycle is coming out to be negative. Okay, the net weight of this cycle is coming out to be negative, which is a problem for us. Okay, this is the problem for us because since this the net weight of this cycle is coming out to be negative, I will actually try and keep modifying this all the three vertices, and ultimately what will happen is your Dijkstra's algorithm will not stop and it will run forever because your Dijkstra's algorithm, it's a greedy algorithm, right? It's a greedy algorithm, and what is the task for a greedy algorithm? To keep on reducing at every step, right? That's the task for a greedy algorithm. So this is the problem for Dijkstra's algorithm. In case of Dijkstra's algorithm, it will try and keep reducing the values until you have minus infinity. All right. So this is a point where your Dijkstra's algorithm will fail. This is the point where your Dijkstra's algorithm will fail. All right. So one easy fix is that you try and maintain your visited array. Okay. So always try to check if that particular node is visited or not. Okay. If that is visited, even if the value is being updated, do not do anything. Okay. If you see that this problem was not there in this. If you think in the previous graph, this problem was not there, although we had a minus 2. The reason was this whole cycle was actually giving me the total positive thing, total a positive number. All right. So since there was no problem because I had maintained a visited array. See, if I have x value here, okay, this will be x minus 2, right? Now I can again visit here and write it as x minus 4. Yes, but since 2 was already visited, I will not again come to this edge. I will not again come to this edge because I have my visited array and I'll see 2 is already visited, so I'll not modify the key value here. Okay, so basically what I'm trying to say is when you have a negative edge weight cycle in a graph, your key values, which are actually the distances of a particular node from the source, those things screw up. Okay, in negative they won't, with a negative edge they might not screw up if you keep the visited array. Okay, they will not screw up if you keep the visited array, but for the positive for a negative edge weight cycle this will be minus sign 0, and then if you come and see this, it will again start getting reduced. Okay, although this 0 is not an answer because practically you're saying that from this edge you're taking minus 5, there it requires minus 5 distance to reach this edge or 0 distance to reach this edge. Okay, so that's why a negative edge weight cycle will actually screw up your solution and we don't want to do that. Okay, so solution for that thing is called as a Bellman-Ford algorithm. Is this understood by everyone? All right. So one way is, of course, you can keep your visited array. So that will help you not go into an infinite loop, not go into an infinite loop. But if your update equation is changing every time now, then it might go to infinite loop. Okay, because update equation is if you're getting reduced uh, value for any particular edge, key value for any particular edge, then of course it will try to run more. Okay, so this is why the algorithm will fail. Okay, so the solution for this is a Bellman-Ford algorithm. Okay, so just hold on for a moment. All right, so we are discussing about Bellman-Ford algorithm. See, so Bellman-Ford algorithm, as you understood that it's a bit of a greedy approach that we are talking about in Dijkstra's, and this greedy approach is actually failing, right? So solution is what? To do things dynamically. Okay, to do things dynamically. So what we'll do is we'll try to use Bellman-Ford algorithm, which is a dynamic programming algorithm. Okay, so this is, since this is the continuation, I would like to teach Bellman-Ford right now. Okay, so this is the first algorithm that we are going to see in dynamic programming. So in Bellman-Ford algorithm, what you're going to do is you initialize the graph for vertex V. Okay, and now distances, all this step is same as Dijkstra's. Okay, preceder this and this, all the steps are same. Okay, now for I equal to 0 till size of vertices minus 1. Okay, for each edge with weight W in this, you'll actually take this. If you check the update thing, and if this is less than this, then you update accordingly. This is what we have done in Dijkstra's algorithm as well. Okay, so no change over here. You keep on doing this. Okay, but you restrict your I values to V minus 1. Okay, now you have to check for negative edge weight cycles. Okay, so what is happening is you run your Dijkstra's algorithm in the worst case on every vertex. Okay, so you are sure since every vertex is covered, I am fine with that. Okay, you'll not run it more than this times. All right, so this is where we limit the number of iterations it the Bellman-Ford algorithm will do. Okay, now next thing is, if there is a negative edge cycle, so what you do is simply do one more iteration for all the edges. Okay, so for each edge, if this is still coming out to be less than this, okay, then the graph contains a negative edge cycle. See, the reason is One moment. So in this algorithm, what was happening was once this guy and this guy done, what this guy and this is also processed. Now, if two people who are already processed, okay, see when I say something is processed, that means the distance that I'm getting in that case is the shortest distance from the single source, shortest distance from my source, right? Now, if this particular edge is again reduced, the key value of this particular vertex is again reduced, or this vertex, if it is reduced, then what is happening is there is something wrong in the graph and we have a negative edge weight cycle. Okay, so because if you calculate the sum of this will be -2. Again, if you run -4, again if you run -6. So your the distance from the source is getting reduced for a particular vertex after your Dijkstra's algorithm is over. This means that there is a negative edge weighted cycle. Okay, when I say negative edge weighted cycle, see there are two things. One is saying negative edge weight, EDGE. Okay, negative edge weight, and second is negative edge weighted cycle. Wow, I have introduced a different way of writing D and G together. Interesting, right? Negative edge weighted cycle. Okay, good. So there are two things. One is this and the second one is this. Now, when you have a negative edge weight cycle now, so Dijkstra's algorithm can keep reducing number of nodes, the weight of every node to minus infinity. Okay. So when you have this negative edge weight, that means the sum of the particular cycle is negative. Okay. Negative edge is okay. Maybe some of the edge is negative. It's all right. But negative edge weighted cycle means that there is a cycle in which the total sum of all the weighted edges, is nothing coming out to be but negative. Okay. This is why this is a problem for in case of Dijkstra's algorithm. Is this point clear to everyone? Right? So this is what is happening, and I hope the Bellman-Ford algorithm is also clear. So you basically in this algorithm now you limit your number of iterations that are happening. Okay, so this is the extra part that we are doing. For every particular edge, you will check if still some weight satisfy this condition. Okay, if still some weight satisfies, because when you keep on running this now, so it will happen that few of the edges are coming out to be negative things. Okay, so Bellman-Ford algorithm actually tries to help you out with identifying whether a particular tree has a particular graph has a negative edge weight cycle or not. Okay, if it has a negative edge weight cycle, actually, so the single source shortest path is not, you actually cannot find using the uh, you can say the normal Dijkstra's algorithm. Okay, you need to make some modification so that you get the correct single source shortest path, right? So this algorithm is used to find whether a particular graph has negative edge weight cycles or not. Is this algorithm clear to everyone? All right, so let's see the time complexity of this. See, now Bellman-Ford runs how many times? See, simply we were saying for every edge, okay, for every vertex in the graph, okay, and for each edge connected to a graph. If you see point number 2, not 3, but point number 2 if I visit. So they're saying for every vertex in this and for every edge, okay, for every edge u comma v, you have to do this. Now see the difference over here is you're actually running it for on all vertices. Okay, if there are 10 vertices, you're doing it 10 into number of edges which are there. Okay, so this is not for each edge in a particular vertex. It is not that. So every time you collect, you have one vertex, and every time you're running for all the edges. Okay, this thing. Is this clear to everyone? So that's why the time complexity here becomes V into E, or worst case it will be V cube. Is this clear to all of you? Yes or no? The time complexity. Okay. So this becomes order of V cube in a complete graph. All right. Okay. So with this, I have actually completed your greedy algorithm. Okay. So now what we are going to do is we are going to solve some gate problems which have come from greedy algorithm and MSTs in the past 6-7 years. Okay. And once we complete those the gate problems, next thing that we are going to see would be dynamic programming. Okay. That will be the last topic in algorithms. So let's try and solve some problems, gate problems on this. Okay. This is your first problem. Now again, just try this problem. Once you complete, let me know. Anyone else who completed this problem? Anyone? Okay. So let's see the solution for this. All right, so let's see the solution. So in this, what we're saying is I need to find the number of distinct minimum spanning trees, MST, for the given weighted graph. Okay. Now, try to think of Kruskal's algorithm. Okay. For any graph, there are two algorithms, either Kruskal or Prim's. So I'll say if I don't talk about time complexity and all, I will say Kruskal's algorithm is much better to use in case of numericals compared to Prim's. Okay. Kruskal's algorithms is much better for problems. Okay, so if I have a minimum spanning tree for this graph, first of all, the edges, I'll say the edges with minimum weight should always be there. Something like this edge will come. Okay, then this edge will come, then this edge will come. Right? Will this edge come? Yes or no? This one? Yes, it will also come. Yes, because no cycle is being formed till now. Okay, this edge will also come. Okay, yeah. So I've taken five edges and all of them will come. And the thing in these five edges are that all the edges have minimum weight. That is one. Clear to everyone? Sai clear? Now I'll talk about edges which may come or may not come. Okay. So this edge, will this edge come? This edge can never come, okay, because it will actually create the cycle and it has more weight, so this edge will not come. What about this edge? This edge also will not come, correct? Now, will this edge come always, yes or no? It will always come, okay. There is no other way to say that it will always come. The reason is that this edge actually connects the two vertices which were never connected before, okay. Now, now see, I need to connect this part and this whole part, correct? So I can use what? Either this or this or this, correct? Any of the one edge will be sufficient for me to connect these two parts. So that means three choices over here, three choices over here. And remaining, this part and this remaining part I can connect using either this edge or this edge. So two choices over here. Yes, never connected. See, because MST is what? Is a it is a tree, right? So tree should be connected, of course, right? It should be connected, right? So now once you connect them, if you take any more edges out of these three now, just take one edge. Now if you take any more edges, they'll form cycle. Okay? Something like, let's say if you take this edge. Now if you take this edge, they'll form cycle. If you take this edge, it will form cycle. Alright? So that's why. So three options in the upper part and two options in the lower part. Okay. So 3 into 2. Total, I have six options. So in six different ways, I can choose my edges so that I can get the minimum spanning tree. And the reason is C, because all of them have the same weight. So I have options over here. Understood everyone? All right. Okay. So let's move to the next question. All right. Try this problem now. So, Sanjeev, if you look at the question, okay, the question is asking minimum possible sum of weight of all eight edges. So I think you have only given me the partial answer. Yeah. So be careful what you have to calculate. Yeah, all eight. Because this is a numerical based question. So even though you took the right technique, you'll get the wrong result. Sai, have you completed this? Okay. So let's try to solve this problem now. Okay. Okay, 1 minute. Okay, take your minute and then we'll discuss this problem. All right. So now in this question, what they're asking is that I'll tell you in summary what the question is saying. They have given you some weights, okay, and they have not given you few weights of the edges, okay. Now the weights which have been given, they are saying that these all edges are part of the minimum spanning tree, okay. So I have how many? 1, 2, 3, 4, 5, 6 vertices. So that means I'll need 5 edges. So this is the minimum spanning tree given. So what they want is you have to find the weight of all edges. So basically I need to find this value and this value, okay, such that the minimum spanning tree is not disturbed. That's my goal. And you have to find the minimum possible sum of weights, okay. So let me say if I take value here 7, will 7 be okay? Yes or no? No. The reason is if 7 is okay na, then I should include this as the MST rather than this guy, right? So that's why 7 is not okay. How about 9? Is 9 okay? No. This is the reason. Distinct integer weights. Okay? 9 is also not okay. So it should be greater than 9. So the minimum value which is greater than 9 is what? It is simply but 10. Correct? So 10 is the weight. Now if I take 10 of this weight now, this and this will be taken in MST. As soon as you try to take 10, this will create a cycle and 10 will be discarded. So we are good to go. Okay. Now let's talk about 4, 6. So now 4 and 6. So this will be what? 7 in the same fashion. Yes. And in the same way, this guy, this guy should be minimum of 2, 15, maximum, I mean, greater than 2, 15, and 7. So that means this guy should be 16. Size 16. Why 20? If you take 20, I mean, you can take 20, but we have lesser value. I need minimum possible sum, na? Okay. So this will be 16. So now if you take the sum, this will be 10 plus 16 plus 7, which comes out to be 33. Now they are not asking the answer as 33. What they are saying is you have to give me sum of all the weights, all the edges. So this means 33 plus 36, which gives you 69. So your answer is 69. Okay. So I hope everyone is clear on this. So let's move to the next problem now. Now try this one. Try this one. Sai, have you completed? Okay. So let's see the solution for this. Let G be a connected undirected graph of 100 vertices and 300 edges. Okay. The weight of the minimum spanning tree of G is given to you as 500. Now the weight of each edge is increased by 5. Okay. Now the first question is, if I increase weight of an edge, of every edge by same quantity, will this affect my minimum spanning tree, yes or no? If I increase edge of every weight by the same value, will this affect my minimum spanning tree or not? It will affect. It will affect. How? Yeah, okay. I'm saying, will it affect my minimum spanning tree or not? That means whatever spanning tree I'm getting, will that affect the spanning tree or not? I'm not talking about weight, not the weight, spanning tree. Yeah. So basically, if you increase the weight of any you can say of a particular graph, if you increase the weight of all edges by a same quantity, your minimum spanning tree will not get affected, but the weight of the minimum spanning tree will get affected. Okay, weight will increase, of course. Okay, so what I can say is, in this question, okay, same MST will be there even after the change in weight. Okay, MST will not change, but now since weights are increased by 5, so the weight of the MST is also increased. Now, by how much will it increase? See, 500 is the previous weight, and there are 99 edges, and all the edges were increased by a value of 5. So that means the new weight of the minimum spanning tree will be this, which is 995. Everyone understood? Alright, so let's try to solve the next problem. Okay, now try this one. All right, so in this question, P is true, right? The minimum spanning tree does not change, but the weight will change, right? This is true. Now, can you give me an example why Q is false? If you all of you saying A, why Q is false? Just tell me an example, or tell me a fact which will help me understand why Q is false. It is saying the shortest path from between two pair of vertices, okay? Shortest path between two pair of vertices does not change. No, see, Sanjeev, see, I am saying shortest path. You're saying costing between A and B is 40. Okay. So you're saying the value of the shortest path, but I'm saying the path itself. So Q is saying the path, not the value or the cost of the path. I'm not worried about the cost. Cost, of course, will change. I am saying, will the path change? If you're saying A, you have to give me how the path will change, or otherwise D would be the correct answer, right? Aditi, Aditi and Sai, you got A. How are you saying A? See, if you're saying some statement is false, you have to give me a counter example for that. If I say that all edges are increased, okay, so all edges will be increased. That is the shortest edge will be will still be the shortest. So if it is considered that D, then D. Okay, fine. Yeah, it makes sense. Yeah. See, the path will remain same, na? Path will remain same. Cost is increased, I know. Similarly, see, there are two things. I say minimum spanning tree, I say weight of the minimum spanning tree. So when I say weight is changed, but minimum spanning tree does not change. Similarly, two things are there: cost of the path, cost of the shortest path, or the shortest path itself. Okay, so cost will change. Here we are talking about the shortest path. Aditi, are you still online or give me the reason why A? Yeah. So I'll actually tell you guys that A is the right answer in this. Now let me tell you an example of what is happening. Okay. Q part is a little tricky. Okay. Please understand this carefully. So let's say I have this node 1, 2, 3, and 4. Okay. And then you have 5. Let's say this is 1, this is 2, this is 3. Let's say this is 10 and this is 15. What is the shortest path now? 1 to 2, 2 to 3, and 3 to 4. Correct? Now if I increase every edge by 100, this becomes 101, 102, 103, 110, 115. Now what is the shortest path? Now, no, 1 to 5 and then 5 to 4. Correct? So basically, shortest path, it depends on what? It depends on number of edges which are there in that path. Number of edges which are there in path, and when you increase those number of edges, then what is happening is this particular path may change, because there might be some other path which has less number of edges, but the edge weight is more costly than the previous path. So now if you add a very huge number, so this number actually, actually, it is so huge that now the cost, the shortest path depends upon the number of edges which are there. Okay. And see, we are not talking about a unweighted graph. Okay. If it was unweighted graph, then I was okay. That Q is also right. Shortest path will not change because we have different edges for everyone, same edge weight for everyone. But here we have a weighted connected graph, so there is no upper limit to the weight, right? And then they are saying distinct positive edges, and edges are also distinct. If you had same edges now, then this problem will not be there. Sometimes the shortest path will not change, and sometimes the shortest path will you may take a graph where shortest path will never change if you increase the weight. Okay, is this example counter example clear to everyone? So somehow all of you got A, but again, yeah, the explanation was not correct. Okay. So we need, see, any time you get a statement now, anytime you get a statement, all you have to do is Yes, it depends on number of edges. Your shortest path, if you take a very big number which you're adding to your the current weight of the edge, if you're taking a very big number and adding to it, then it will actually depend on number of edges which are included in the shortest path. Okay, if you have less number of edges, then you may get a different shortest path once you make the modification, right? So please make sure that whenever you want to make sure that some statement is false, just try to think of a question or try to think of an example which is a counter example. Okay, if for a counter example you are able to contradict that statement, then definitely that statement will result in being false. All right, so this question was actually came for 1 mark, but this was a very good question. Okay, the Q statement was very good. And I'll tell you one more thing. In MSTs, especially in MSTs, they like to play like this. Okay, they like to play like they have given, I think, 3 to 4 questions like this in past 7 to 8 years, where they will like to play in this manner. All right, so I hope this question was clear to everyone, right? So, okay, so let's call off the class for today. We have aptitude as well. Okay. So next I think I have still 4 or 5 questions that I want to discuss. That will be discussed in the next class. And guys, I think your next class will be scheduled for Saturday. Okay. So we'll not have on Tuesday and Thursday. I won't be available for the classes. So next algorithm will happen on Saturday and then on Sunday. I think I'll finalize timings with Dinesh sir, and then they'll tell you. But mostly this is what will happen. Okay. So you'll have back-to-back classes of TUC on weekdays this time. So weekend we'll study. We'll continue our discussion on algorithms and dynamic programming, and I mean algorithms, and we'll complete these questions and then start dynamic programming from the scratch. All right. Okay, guys, so I hope everything was clear today, and I hope everyone enjoyed today's class. So